In this video, we're going to continue our look at matrix multiplication, this time with a focus on the rows when we multiply two matrices together. Previously, we had a column-based discussion, and one of the take-home messages was that if you multiply a matrix A with, say, the j'th standard basis vector of the correct size, then what it does is extract the j'th column from the matrix A. So we'll flip it around this time, and what we will do is first see how to extract rows from the matrix A. Then we will give another interpretation of the matrix product of two matrices A and B. So we have looked at defining matrix multiplication in terms of the coordinates. Then we thought of it as the matrix A acting on the columns of B. So this time we will add to that an interpretation based on rows. And then I will wrap up this video by connecting our row-based viewpoint of matrix multiplication with a common application of matrix equations, which is setting up and solving systems of equations, in particular systems of linear equations. In this video, we will not go through the methodology to solve that because that would take a long time. That is a separate subject to dive into, but rather I will just connect our discussion to systems of equations. To extract the rows from a matrix, we will actually use this knowledge about extracting columns from a matrix. So dimensionally here, the matrix A is m by n, and in this boxed expression, the standard basis vector E sub j must be n by 1 in order for this matrix product to be defined. However, now what we're going to do is multiply A from the left. So denote by E sub I transpose the 1 by m row matrix, which is the transpose of the standard basis vector E sub I from Rm. Basically, we're going to flip how our standard basis vector looks from a column into a row. And then if I want to multiply A from the left, I have to make sure I'm doing this with the right dimensions. So throughout the computation we're about to write down, let's practice identifying dimensions. It's always a good idea with matrix algebra to make little annotations for dimensions. For example, here, this transpose standard basis vector is 1 by m, and the matrix A is m by n. So that overall this product will be a 1 by n row matrix with n entries. To explain how this matrix product works, what I would like to do is bring in our previous knowledge by flipping the roles here. Notice if I take the transpose of the left-hand side, it is A transpose times the ith standard basis vector. That's what's inside the parentheses here. And then I need to transpose that again to get back to the original left-hand side so that we still have equality. Keeping track of dimensions, A transpose is n by m, it's the flip of A, and the standard basis vector that we're working with here is m by 1, so that inside the parentheses we would have an n by 1 vector in Rn, but we are going to transpose that into a row matrix which is 1 by n. Using our boxed knowledge at the top of the slide, we can say what's inside the parentheses. We are multiplying a matrix with a standard basis vector. So this will be the ith column of A transpose inside the parentheses. A transpose is an n by m matrix. So this ith column is n by 1, and we take the transpose and it's 1 by n. We should always be getting 1 by n for each of the lines in this computation because we have equality here, but again, it's good to always visualize what's happening. Now the ith column of A transpose has the same entries as the ith row of the original matrix A, but one is a column and one is a row. So what I'm going to write down is it's the ith row transposed into a column, that's all inside the original parentheses, and then of course we still have our transpose outside the parentheses. So take a moment to carefully work from the inside out to write down the dimensions here. The original row from A is 1 by n, so you can see I must transpose it to have equality with the n by 1 column from the line above. And then after we transpose everything, we get back to our 1 by n overall result. But now we are transposing a transpose, so the final result is that the transpose of the ith standard basis vector from Rm, multiplying with A on the left, extracts the ith row of A. And of course that is 1 by n. Okay, so let's update our conclusion here at the top. I'm going to replace it with what we've just discovered. We have now a methodology for extracting the ith row of a matrix. See now what you make of this question. Using standard basis vectors, write down an expression that would extract the single coordinate A sub ij from the matrix A. Again, that notation means the entry in the matrix A which lives in the ith row in the j'th column. We need to put everything together. So if we want the ith row and the jth column, then we want to extract the ith row, and then from that, the jth column. So overall, we can say that the entry A sub ij is this triple product. Matrix multiplication is associative, so I haven't put any parentheses here. This matrix triple product is 1 by m times m by n times n by 1, giving us overall a 1 by 1 result, which is the scalar entry sitting in the ijth position from the matrix A. Okay, let's now talk about what happens if we multiply two matrices together. So sticking with the same matrix A, which is m by n, let's multiply that with the n by p matrix B. If I want to describe its ith row, then I'm going to use our information at the top, that the ith row of the matrix A times B can be computed by multiplying A times B from the left with the transpose of the ith standard basis vector as we just did. Let's make a point of keeping track of dimensions. A times B will be an m by p matrix, which means that each row has p entries. So the object that we're computing here is a 1 by p row. Take a moment to write down all of the dimensions for the product of the three arrays that we have on the right. The transpose of the standard basis vector is 1 by m. A is m by n, b is n by p. Agreeing with our computation on the left, this will be a 1 by p row. Matrix multiplication is associative, so let's just group the terms a little differently. But now we recognize that the product on the left inside the parentheses is going to extract the ith row of A. Quick dimension check. The ith row of A is 1 by n, B is n by p, so yes, this will be a 1 by p row. Now we're saying any row, say row number I, of the matrix product A times B can be viewed as the ith row of A times B. That holds for each of the rows, so overall we can write that the matrix product A times B has rows which look like the corresponding rows of A times the entire matrix B. Each of those rows is 1 by p, there are m of them. So yes, overall this matrix product is m by p as expected. Let's now look at an example. So I'm going to give you an explicit matrix computation. We actually saw this exact computation in our original video on matrix multiplication. This was the first viewpoint that we took. I would think of this as the traditional way to multiply matrices, where the entry in the ijth position of the product is the sum of a bunch of pairwise products coming from the ith row of A and the jth column of B. Then in a previous video, we took this column-based viewpoint, where we said the columns of this matrix product can be thought of as the matrix on the left acting on the columns of the matrix on the right. If we think of this as A times B, this is A acting on the columns of B. So this is what I would consider a column-based viewpoint of matrix multiplication, but now we are adding to this a row-based viewpoint. So here the two rows of this matrix product come from the rows of A times the matrix B. If you take a moment to mentally work through any of these computations, you'll see that they all agree as expected. So they're all going to return you the same 2 by 2 matrix, and this is what that matrix is. To summarize, our first viewpoint we actually characterized as essentially a dot product between the rows from A and the columns from B. There, when I say dot product, I'm imagining the rows of A first flipped into a vector so that the dot product is defined, but that's being a bit pedantic. So that action of dot product is what gives us the sum of products. And then we thought of it as the matrix A acting on the columns of B, where the matrix on the left times the columns from the right defines the columns of the product. And now we're saying, well, if you want to compute the rows of the product, you can do the rows from the left times the matrix on the right. We are going to now step away from the idea of multiplying two general matrices together. Let's refocus our attention on multiplying a matrix with a vector. I would like to take a moment just to connect ideas from matrix multiplication to systems of equations. For example, here we have a system of two equations for three unknowns, x1, x2, and x3. We can recognize the numbers 1 to -1 as entries in a 1 by 3 row. And similarly from the second line, 1, 1, 1, the coefficients in front of the unknowns x1, x2, and x3 could also be seen as entries in a 1 by 3 row. So we can reorganize this information into matrices. We can interpret the equation x1 plus 2x2 minus x3 equals 7 as the row 1 to -1 times the vector x equals the entry 7. And similarly, x1 plus x2 plus x3 equals 0 is a row 1, 1, 1 multiplied with the vector of unknowns x, and that product equals 0. So on the left, I've written the rows times the vector x as a 2 by 1 vector and set that equal to the vector 7, 0. But more typically, we write the expression on the right, where we have the matrix A, which is a 2 by 3 matrix of coefficients, times the vector of x consisting of the unknown quantities x1, x2, x3, equal to the vector b, 7, 0 of constants from the right-hand side. For the rest of this video, I am not going to talk through the methodology behind how to solve this system of equations. I just want to introduce in some terminology and visualization. So the solution to this kind of equation is the set of all vectors x in Rn, here it would be R3, which satisfies all m equations. In general, for a system of equations like this, which can be written in this matrix product form, Ax equals b, the solution set is either empty, or consists of exactly one element, or contains infinitely many solutions. I will visualize that for you. In this particular scenario, where we have more variables than equations, you would either be looking at no solution or infinitely many solutions. Let's think of the left-hand side in terms of our row-based interpretation of matrix multiplication. We could take the matrix of coefficients A and think of it as m 1 by n rows, so that when we multiply A with the n by 1 vector of unknowns x, we produce an m by 1 vector whose rows look like the corresponding rows from A times the vector of unknowns x. I've used this terminology before, but I really want to highlight it here. So each row is what we call a linear combination of the unknowns from x. A linear combination of x1, x2 through xn means to take those, scale them by numbers, and add them together. So here the coefficients, or the weights, come from the matrix A. Then when we bring in the right-hand side B, what we do is we create a system of equations, but you could call that a set of constraints. These are called constraints because they restrict the possible values in the solution set x. The vector x must satisfy each of these equations in order to be considered a solution. So to summarize, each row is what you could call a linear constraint. Here I'm providing you with an example of the idea of a constraint, but this is not the definition of a constraint. So there are many other types of constraints that you can encounter in mathematics, and some of them are, say, inequalities rather than equalities. So here we are looking at a specific type of constraint. Geometrically, each of these rows defines what we call a hyperplane. So a hyperplane looks like a line in R2 or a plane in R3. And in general, any equation of the form c1 times x1 plus c2 times x2 plus all the way through cn times xn equals a number, that defines a hyperplane in Rn. So here I tried to give you a general form, not based on the matrix A. So we can think of these hyperplanes as visual objects, lines in R2, planes in R3, and the solution to the matrix equation Ax equals b geometrically is the intersection of those hyperplanes. Let me give you an example. Going back to our system of two equations for three unknowns, I'm using the coordinates x1, x2, and x3 to represent the unknowns, but since we have three of them, you could think of those as x, y, and z in xyz space. So here x is just the coordinate x in R3. Each of these equations defines a plane in three-dimensional space. The word plane here specifically refers to this kind of object, but in general, we could think of them as constraints. Just so happens that this very specific type of hyperplane is also just called a plane. So if you consider a triple of coordinates x, y, z in R3, in order to be on the top plane, you would constrain your attention to coordinates that satisfy the first equation. So it would have to happen that the x coordinate plus twice the y coordinate minus the z coordinate is 7. And likewise, to be on the other plane, you would constrain your attention to x, y, z coordinates whose sum is 0. To solve this system of equations, in other words, to find a solution to the matrix equation Ax equals b that we set up, is to identify this line of intersection. So in this particular situation, we are looking at infinitely many solutions to the system of equations because there are infinitely many points that live on this line. Let me wrap this up by visualizing the possible solution sets for a system of two equations with two unknowns. So here the matrix A would be a 2 by 2 matrix consisting of the coefficients A11, A12 along the first row, A21, A22 along the second row. X1 and X2 are unknowns, and we could be interested in solving this equation given specific values for B1 and B2. Each of these equations defines a line in R2, so a line in the xy plane. Let me first visualize what exactly one solution would look like. So each of these algebraic constraints visualized in the plane turns into a line. Again, that's like a hyperplane in R2. And if they intersect exactly once, then we have exactly one solution to the system of equations. Take a moment to sketch what it would look like to have either no solution or infinitely many solutions. For no solution, we want to draw two lines which don't intersect. So those would be parallel. And then we already saw infinitely many solutions when we have two planes which intersect in a line. In R2, with two coordinates, we need to have two lines which intersect in a line. So here's the first one and there's the second. I will wrap this discussion up here. So I hope you enjoyed this row-based interpretation of matrix multiplication as well as this detour into systems of equations. Thank you for your attention.